Let's welcome Line Roald. So Line is an assistant professor in the Department of Electrical and Computer Engineering at the University of Wisconsin-Madison. Please share the screen. Okay, that's good. And you're ready to go. Thank you, Line.
All right. I think I also managed to unmute my. Can you hear me? Is this
working? Yes, all good.
All right, great. All right. So yeah. So welcome to this presentation. Thank you all for being here. I appreciate this and for the session that you're hosting here. So yeah, this paper is called the Stochastic DC the name of the paper is Stochastic DC Optimal Power Flow with Reserve Saturation. This is joint work with Rohit Kannan, who's a postdoc at the University of Wisconsin-Madison, Jim Luedtke, who's a professor there, and myself. And so as you can tell from the title of this paper, what we're going to look at here is stochastic DC optimal power flow formulation, similar to many of the other presentations that we've seen here already. But kind of one of the key points here, part of the title, which is reserve saturation. And I'm going to explain more what we mean with that in just a second. But first, I wanted to talk a little bit about the motivation. What was it that was driving us when we were starting out writing this paper? Sorry, I'm having some trouble with my slides here. Okay. And so essentially what we wanted to achieve when we started writing this paper was that we wanted to look at this case where we are able to give more responsibility to wind power plants. And in particular in systems which have a very high wind power penetration, it's important that wind power plants are not only providing energy for the system, but that they are also starting more responsibility in terms of providing also balancing energy and reserves for system operations. And so this type of requirements are starting to enter into different codes and systems where there is a lot of wind. So for example, in Eginet in Denmark or AirGrid in Ireland. And it's been shown that it is technically feasible, both in the field and in theory. But sort of one of the interesting things when we start thinking about how we can use wind power plant to provide both generation and ancillary services is how are we going to split the available power between generation and reserves? And so you can think about this here. I've just drawn a little sketch here. You have power, which is the amount of available power that is going to be there from the wind power plant is going to vary over time. And so since we have to manage this variability in the wind power, if we also want the wind power plant to provide not only generation, but also reserves, we have to manage the situation where in some cases we might have too little generation, other times we might have too little reserves. And so essentially, for example, you could imagine if an operator chooses to schedule the wind power plant to provide this amount of generation here, there might be settings where the wind power plant simply doesn't have enough generation to provide what it was scheduled to, and it might dip below level. And there might be other cases where you actually have more available power scheduled. And so what we want to ensure, our goal is that we should be able to use the full range of power from the wind power plant in the most effective. All right. And so that takes me to, this takes me to the second part here of the talk. Can you still hear me? I just got a message on my screen here saying my internet connection is unreliable.
We can hear you.
All right, okay, great. So essentially managing reserve saturation. So let me explain kind of what we mean by this. So when we have typically the way we model reserve activation in response to wind variation would be the following way. So we say that the power that we're going to get from a power plant is going to be equal to some scheduled amount of PI0 here, plus an adjustment that happens in order to balance, have a power imbalance here. And essentially, so this power imbalance that arises due to, for example, variations in wind generation, due to variations in load or generation outages, that power imbalance gets across the different generators according to a participation factor. And so when we're looking at this function over here, what you see here is that, if you think about generation as a function of this power imbalance, we get this linear function, the slope that is equal to the participation factor. Now, the problem is that generators, of course, also have a generation. And so the problem that can arise here is that we might be asking the generator to produce more than its maximum limit if this power imbalance is large. And so we have to find out a way of dealing with this. And one way of doing this is that we simply just change the participation factors and we reduce the slope of this response in order to make sure that we are not going to cross over by this maximum wind power here. But in order to do this, we have to leave some open room here so that we are sure that we are not going to hit this, because we don't know how large this wind power imbalance is going, the power imbalance is going to be. We might need to leave some room here to make sure that we never hit this maximum limit. And when we're talking about this in the context of wind power plant, we have an additional issue, and that is that the actual upper amount, the maximum available amount of power is also uncertain. So it's not only that the power imbalance is uncertain and we might be varying in this range, the maximum power available is also uncertain. And so we have to take that into account as well. And that means that this approach get really conservative. However, so I will also say this is typically how we have literature. So what we are planning on here is that we would like to introduce what we call saturation. So essentially here, the idea is that we can follow this slope, the original slope that we might have found to be optimal, all the way to the maximum power. And then as we are reaching this maximum power, we're just going to stick around at this maximum level of generation that we have available. And this allows us to use the capacity to the full. So let's see how we are going to model this in our problem. So essentially, if you want to model reserve saturation, we end up with a kind of a piece function like this. So if the power imbalance is small, then or if it gets negative here, then we will be stuck at our lower generation bounds. For intermediate power imbalances, we're going to follow this linear curve. The upper level here, we're going to be at that maximum power level. So essentially, we have this three-part curve. And in the middle here, this is our target generation that describes this curve in the middle. However, the problem here is, of course, that if we only use this linear function, we might be in a situation where we are missing generation. So if I ask a generator to operate up in this region, now it's only going to operate, it's going to produce less than what I asked it for. And so I somehow have to account for that. And so we're adding this second term here in the target power generation to make up for this missing generation piece. All right. So this might look good, but now the question is, how do we implement this into an optimal power flow? There's clearly several issues here. For example, this generation saturation curve is a piecewise affine curve. It's non-convex. You know, how are we going to deal with this? But first, so what I'm first going to do here is I'm going to formulate this problem as a two-stage stochastic optimal power flow, and then I'm going to talk about how we're going to solve this. So our stage here in our two-stage problem is that we are going to determine the generation schedule and the reserve capacities. And then in the second stage, we're going to minimize the use of reserves and line flow violations. So I'm going to first talk about the first stage, and then I'm going to get back to the second stage later. Okay, so first stage of this problem, what does it look like? So here I have an objective function, and in this objective function, I have two terms. The first term minimizes, which is marked in green, minimizes the cost of scheduled generation and reserves. And then there's the term marked in blue here minimizes the cost, the second stage cost. And I'm going to come back to that second stage problem in a minute. Then I have a constraint here that tells us that scheduled generation is equal to the expected load in the system. And then I'm also, I also have another, I also have another constraint that determines that the scheduled generation and reserve should remain within generator bounds. And then I'm going to require that the subset of my generators will have to provide reserves. And this in order to make sure that the generators, there's always one generator that is available in order to adjust its generation. And then I also have this constraint, which represents a minimum and a maximum willingness of the operator to actually schedule generation from a power plant. And this is particularly important in the case of wind power plants, because the system operator might sort of set, for example, as an upper limit here, might say, okay, we are not going to schedule more power from a wind power plant than the, for example, the forecasted power. All right, so in the second stage cost, what we are doing is that we're taking the expectation over a range, over the stage, the cost of the second stage. So here we're taking the expectation function Q. So function Q, lowercase q, depends on the first stage variable, P0, R plus, R minus alpha, and also on the realization of the wind power injection. And so this Q here is the optimal solution to this optimization problem that you see here at the bottom. So we have an objective function, which is essentially the penalty for exceeding the procured reserve. So that's the first part here. So essentially, if we don't schedule enough reserve capacity in the first stage problem, we might exceed our the generation that we had planned for and the reserves that we had planned for. And if we do, we are going to incur a penalty. And then we have a second term, which penalizes the line flow violations. We also have here a set of constraints that describes our reserve activation. And then finally, at the bottom here, and I hope you can see this, there is the equations that describe the power flows. You might have noticed in the first stage, we didn't really talk about power flows at all. In the second stage, we do have the power flow, the DC power flow representation of the flow throughout the system. All right. So what is kind of an to note here is that the second stage solution is really uniquely determined by the first variables. And so what this means is that as soon as I fix the generation from the first stage variable, I also fix the generation, the reserve capacities, participation factor alphas, and I given an uncertainty realization. Our second, we can actually solve this stage problem as just solving a problem. I mean, it's really no more degrees of freedom. So what I really have to solve for then in the second stage is to find this variable S here, S of omega, which determines how large is this part that I'm gonna have to, you know, how large is this power that I have to distribute across the generators. And it is kind of a little bit tricky to find this S because it is not just exactly the same what we are missing from the other generators, because the alphas here are, they are determined to sum to 1. So finding this S is actually an iterative process. So it's a little bit complicated to find it, but we'll come back to that. So essentially this is our problem now. And the question becomes how to solve it. Because what I have just shown you is a non-smooth, non-convex, two-stage stochastic optimization problem. And for anyone who have tried to solve any of this, we know that that can be challenging. And specifically, I would claim that this is the reason why we haven't been looking at this problem with reserve saturation, because it's really just, I mean, it's hard. But the good news is that we found a way of doing it. Okay, so let me take you through this. So our solution approach, the first thing we do is that we create a smooth approximation of our function. And so essentially you see that here, this generation function, and essentially what we're doing when we're smoothing this is that we're going to smooth over these corners here. So we're going to make the corners a little bit more, we are no longer going to have that hard edge up here. We're going to smooth them out. And you can tell that as we are smoothing, we are still maintaining generation within the bounds of the generator. We are just like kind of taking away the fact that it's no longer linear. So smoothing it out here still makes it feasible for the generators. Actually, it's also important to notice here that this smoothness is in order to make sure that we are able to make gradients of this function everywhere. And so we can have a very small amount of smoothing. In fact, the smoothing that we're using is actually this red curve. So you're not even really seeing that it's getting smoothed here. Okay, so that's a smooth approximation. So the second part here is that we're gonna stationary solution using a projected stochastic gradient method. And in this projected stochastic gradient method, what we're doing is that we're starting with an initial guess for our solution X. We decide on a number of iterations T that we are going to use. We decide on what is the mini batch size. We are going to decide how many samples are we going to consider in each iteration, and then we decide on the step length. And I'm going to say here, I'm describing the algorithm with a step length that is constant, but in reality, we had a step length that was also adaptive. So what we're going to do is that we're going to go through each of these iterations. So we have each iteration, and then we're going to go through each sample in our mini batch. And for each of these cases, we are going to draw a scenario for omega, and we're going to solve a second stage problem using bisection search. So this is how we are finding this variable S of omega. We're going to use a bisection search to find that. And then we are going to compute the stochastic gradient of the objective function given our omega and x. then finally, so I had simplified here a little bit. There's a little bit more details in the description in the paper. But then after we have done this whole iteration for all the samples in a mini batch, we're going to go back and we're going to look at, we are going to take a projection. So we are going to make a step where we are averaging the gradient across all of the samples that we had in our mini batch. And we're going to make a step. And then we're going to find a new x. And then we're going to project that x back onto our feasible set. And then after we've done this, we are going to estimate the objective function of this problem using an independent sample of omega. And then we're going to check our termination criteria. And essentially how this method terminates is that after we've done the number of iterations that we wanted to do, we are just going to return the iterate with the smallest objective function, estimated objective function as our solution. This is how we do it. All right. So now the question becomes, how well does this perform? So what we are going to do here is that we are going to prepare our method, which is the smooth approximation with reserve saturation, to a problem that uses chance constraints. So here we have no reserve saturation, and we are limiting directly the probability of violation. We are also going to see that we are going to look at a problem where so that's the first problem we're going to benchmark against. The second problem benchmark against is where we're just going to use a generation penalty. So it already came up here that chance constraint only limit the probability of violation. So here we're going to, instead of limiting the probability, we're going to penalize what happens if we are asking the generators to generate power above its maximum limit. So here again, in this third case, we are not considering reserve saturation, but we're just going to penalize this deviation here. What is important is that as I'm now going to go through this, we are always going to include reserve saturation in our model as we're doing the evaluation. And this is because we believe that reserve saturation is the really true model of how the power system would respond to uncertainty.
Well, Lina, it will be good to conclude soon.
Yes. So yeah, let me just take you quickly through this. Okay, so just going to show you some results from a 6-bus system. We have 10% load uncertainty. Here in blue, you see our smooth approximation. The black points are the chance constraints, and the generation benchmark is shown in red here. What you're seeing here is that on the x-axis, we have expected generation cost. We have probability of line violations over here. So essentially, we would like to be down here in the corner. And what you can tell here is that our smooth approximation really kind of draws out a Pareto front here. So you see that it performs the chance constraint in most cases. It's possible to get a similar performance as with the generation penalty in most cases, but the generation penalty requires more tuning because you have to tune both line violation penalties and penalties on the generation. So in the case where wind generators can provide reserves, this is what we see. If you are looking at a case for the same system where wind do not provide reserves, what we see, but they are dispatchable generation, we see that there is actually a gap, and the smooth approximation is able to find these solutions that both of the other problems are not able to find at all. So in this case, it really outperforms both of the two other methods. And if we also consider the wind generators to be non-dispatchable, what we see is that actually there is maybe not that much anymore, at least for this system. And so here the performance is kind of similar. So what this means is that this method becomes really important as the wind generators are starting to take on more variability in the system. So I also just very quickly wanted to conclude with a 118 bus system with 25 wind power plants, just to say we can run this for larger systems. What we see here is that, I mean, we are solving the same problem. We're just picking the lowest cost solution, which has line flow violations smaller than 0.5%.
I lost Lina. Can anybody hear me or?
Yes, Maria, we can hear you.
We can hear Lina.
But can you hear Lina, or is it only me?
No, unfortunately not.
Okay. Okay, let's wait 1 minute. Okay, maybe I would suggest maybe to move on to the next presentation, and then we can catch up with questions for both papers at the end, just in case Lina does not appear in the next minute.
So Lina has a problem with her network connection. I'm speaking on the phone with her. So
excuse me, what did you say, Femi?
She has a problem with her internet connection.
Yes, I guess so. So
yeah, she's saying that
if she doesn't appear, just to keep the schedule, I think if she doesn't appear in the next seconds, maybe we can go with the next presentation and then sum up all the questions in the end when she is available. Okay, let's wait a couple of seconds and then we can move on with Ilya. Okay, let's do it. Let's play the recording for Ilya, and then we. Lina, you're back.
Oh yeah.
Okay.
Yeah. Okay.
Okay.
So
okay, sounds great.
Sorry about that.
It was a nice.
Yeah.
No, it was a nice talk. I have one question from the audience. Nawaf Najir asks if instead of smoothing the generation penalty, we use integers to turn the problem into MILP, would that make it easier to solve?
I don't believe so.
Yeah,
I wouldn't believe so. I think it's a very, I mean, so essentially the way we are able to get around this is that we are actually solving the second stage problem, which then would become the MILP. We are solving that, it becomes a bisection search. So because we are able to do that, we are able to solve that second stage problem very, very efficiently. So I mean, the way this problem is set up now, there is really no, I don't think that would give a benefit. Okay. Because it's just solving a set of equations as it is now.
Okay, I would have a question regarding the parameter epsilon that you have that is actually providing the minimum participation factor. So this is a design parameter, right?
Yeah. So where does that?
Would this influence a lot the results if you decide in a heuristic way what this epsilon would be, and why really you do have to take such an epsilon? Because since you have the summation of alpha to be 1, for sure some of the generators will have some reserve.
So this is a matter of this type of method requires that you have a relatively complete recourse. So you need to be able to find a feasible generation solution. And you could imagine that if you are, I mean, and there is a problem here, right? If all of the generators reach their upper bound, if you have a huge power imbalance and all of the generators reach their upper bound, then you're no longer able to balance the system, right? And so by having these small epsilons at some of the generators, what you are ensuring is that there will be some generators always available to take up the slack of balancing the system. So this is also maybe even more important than for the end result. It is important as you are solving the problem, because otherwise you might end up with intermediate infeasible solutions. So we could, I think, I mean, theoretically say we could, have this parameter kind of for all the generators, and then we could set it to 0 afterwards. I think that would still work. So it's just a parameter, you would set it pretty small, and you can kind of set it, I mean, you can put it very, very small. So,
Okay, thank you, Lina. We are running out of time. We can move on to the next one. Thank you very much for your
and talk. Sorry for dropping out here.
No, it's all good.